Thank you, Mike. Good morning, everybody, and thank you for coming. The outline of this tutorial will be as follows. I'll give a brief overview of selected Nyquist ADCs. Then I will discuss the issue of creating and interpreting ADC spectra. Then I'll move on to simulation techniques applicable to oversampling converters, and especially the use of RF analysis in oversampling ADC design. Finally, I'll conclude with some references. A to D and D to A converters form the interfaces between the real world, where things are continuous in time and amplitude, and the virtual world, where time and amplitude are discrete. A typical A to D conversion process goes as follows. The input, after suitable anti-alias filtering, is sampled. This results in a discrete time signal, and then quantized, which results in a signal with discrete amplitude levels. These levels can therefore be encoded with a finite number of bits. So when one says an A to D converter, one is basically referring to this whole gamut of operations: sampling, quantization, and encoding. ADCs and DACs are complex mixed signal systems and can therefore be simulated at several levels: at the functional level, at the block level, the circuit level, or a mix and match of these approaches. A functional behavior simulation is often important in full chip or SoC functionality verification. Second order effects are not important or perhaps not needed in such simulations. Block level models enable architectural exploration, what if scenarios, rapid estimation of mismatch effects, and a mix and match approach combining behavioral and transistor level simulations help isolate problems, especially during debug. However, I would always strongly recommend to run the full layout extracted design at the transistor level, because what you did not model is what bites you most of the time. ADC architectures are broadly classified into Nyquist and oversampling converters. Nyquist converters belong to the flash, folding, two-step, pipeline, or successive approximation types. In this tutorial, I'll briefly touch upon the flash, two-step, and pipeline approaches and the oversampling approaches. Similarly, D2A architectures are also divided into the Nyquist and oversampling types. Due to paucity of time, they will not be covered in this tutorial. The first operation, as we saw in the analog to digital conversion process, is sampling, and essentially involves holding an input voltage on a capacitor. This can be done in two different ways: either top plate sampling, as shown here, or bottom plate sampling, where this switch is opened first. In either case, the mean square noise due to sampling is kT on C. Once the signal is quantized, is sampled, it is then quantized. The quantizer has an input-output characteristic as shown in the black staircase. Being a nonlinear characteristic, it is still possible to write V out as V in plus some quantization error. Since the quantization error is a complicated nonlinear function of the input, it's often assumed to be a noise-like signal with a probability density function which is uniform in minus delta by 2 to delta by 2, where delta is the step size. Further, one assumes that this noise is uncorrelated with the input, and given that we've made two completely wrong assumptions, it doesn't hurt to make a third, and that is to assume that quantization noise is spectrally white. Any real quantizer, of course, will not be the ideal staircase. One form of error is an offset error, where the actual staircase is shifted to the left or right, and this is usually very benign. The next form of error is gain error, where the slope of the staircase is different from the ideal slope. However, all steps are of the same size. In reality, of course, the step sizes are all different, and this difference in step size is quantified in two ways. One is what is called the differential nonlinearity, which quantifies the deviation in the step size from the ideal step. Another way of looking at it is what is called the integral nonlinearity, which quantifies the deviation of the transitions of the actual quantizer from that of the ideal. The INL can be obtained by computing a running sum of the DNL. Those covered the static performance metrics. Dynamic performance is often characterized by the signal to noise ratio, and as is well known, when one excites a quantizer with a full scale sinusoid, an n-bit quantizer will result in a peak SNR of 6n plus 1.76 dB. Intuitively, this makes sense because increasing the resolution by 1 bit reduces the step size by a factor of 2, meaning 1/4 the noise power, which is 6 dB. The signal to noise plus distortion ratio, or the SNDR, is the ratio of signal power to everything else, and when you have a real quantizer, it's often, you'll often see this number floating around. It's the E knob, or the effective number of bits of the quantizer. And this is computed by backfitting E knob from the SNDR formula and is given by SNDR in dB minus 1.76 by 6.02. Another dynamic performance metric relevant especially in communication is the spurious free dynamic range. This is the ratio of the peak input signal power to the highest spur sticking out of the quantizer noise spectrum. One of the most fundamental and straightforward ways of performing A to D conversion is to simply compare the input simultaneously with a bunch of references. This forms the basis of the flash analog to digital conversion technique. It's clear that you need approximately 2 to the n comparators to get n-bit resolution. Unfortunately, this simplistic block diagram doesn't work in practice because of clock skew. Once you have an array of comparators, routing the clock from comparator 1 to comparator 2 to the n will cause clock skew. This means that different comparators will sample the input at different instants of time, thereby causing poor performance when the input frequency is high. To solve this problem, a track and hold is inserted up front. The track and hold does two things. One, it provides a held signal to the comparator array, and this causes clock skew effects to be minimized. Further, it provides a benign input impedance to whatever stage is driving the ADC. Since comparators have offset, there is some offset correction circuitry that's necessary for good static and dynamic performance. The back-end logic takes the 2 to the n bus of digital codes from the comparator array and converts it into an n-bit code. During the design phase, the back-end logic, whose design is fairly straightforward, is an ideal candidate for design abstraction. A typical flash ADC design would flow as follows. First, one would design a comparator with a sufficiently low static and dynamic offset. One would then make sure that the comparator regenerates sufficiently fast, and then design a track and hold which is capable of driving this comparator array with sufficiently low distortion. The track and hold design is quite tricky and depends significantly on the comparator architecture. One can then go and design the back-end logic to process the digital outputs of the comparator. One of the issues while designing a track and hold is that it must be designed keeping the comparator in mind. However, if one has a large number of comparators, simulations tend to take a lot of time simply because of the large transistor count in the circuit. So while iterating on the design, this is a trick that I like to use, which I call the current controlled current source trick. Here, a current controlled current source shown in red measures the current going into a comparator and multiplies it by n minus 1. This way, this is a very good model for the load of n comparators while having only one comparator at the transistor level. This is good during design iteration where the track and hold has to be repeatedly iterated to account to be able to drive these comparators with sufficiently low distortion. Recognizing that increasing the number of bits while using a flash would require an enormous number of comparators, the two-step flash ADC has the motivation of trying to reduce the number of comparators in a flash converter. The basic idea is the following. In a flash ADC, it's only comparators which are near the input which give relevant information. So if one could use a coarse A to D converter to estimate where the input approximately is and use a fine ADC to digitize the difference between the estimate and the actual input, then one could achieve high resolution using a lot fewer comparators. An implementation of this idea is shown here. The ADC and the DAC result in a coarse estimate from which the input is subtracted, resulting in a residue signal which is significantly smaller than the full scale of the input. Therefore, the total number of comparators needed is only 2 to the NC plus 2 to the NF. However, the resolution achieved is NC plus NF bits. One problem with the two-step flash is that the fine A to D converter sees a very small input signal. This places excessive demands in the linearity and noise of the fine ADC. To prevent this from happening, one can increase the input of the fine ADC by putting an amplifier, and this way, once the residue is amplified, the noise requirements on the fine ADC become smaller. This is the principle of the pipeline A to D converter, where what one does is to actually implement the fine ADC also based on the same principle, that is, it's a recursive implementation of the two-step. So a pipeline ADC design would have a cascade of stages where each stage generates a coarse estimate, subtracts it from the input, amplifies it by some factor, and then passes it on to the next stage. Every stage is implemented using switch capacitor techniques in most state-of-the-art pipelines. And given the repeated scaling of technology, state-of-the-art pipelines also use sophisticated algorithms to cancel or correct for errors in the ADC, the DAC, and the amplification. A typical pipeline ADC design flow would first explore the design at the behavioral level, where one would calculate the number of bits per stage, the op-amp gain necessary, the linearity and bandwidth needed, and so on, and also investigate digital calibration algorithms that help realize the specifications. Once that is done, the stage design is done with the op-amp, the coarse ADC, and DAC, and pipeline ADC design is quite a mature area, and expert designers will often be able to do this with a spreadsheet in the sense that they'll be able to estimate how many bits you need per stage, the requirements and the gains and the bandwidths and so on, and then just get to designing the individual blocks. An example of a pipeline ADC stage is shown here. It consists of the coarse ADC, the DAC levels, the amplification. All of this is built nicely into one module, which you can simulate very, very carefully, and then perhaps use this as a behavioral model for high-level simulation. Okay, so we have seen, we've got a basic idea of Nyquist ADC architectures. The next thing I'd like to discuss is how do we go about testing this architecture in simulation. We take our cue from amplifier design. So when we want to test an amplifier, we typically put in a sinusoid and look at the periodic output of the amplifier and perform a Fourier analysis of the output. The Fourier coefficients give us information about distortion, bandwidth, and so on. We'd like to do something similar with an ADC. However, an ADC is a bit more complicated in the sense that the output is a sampled output. So we need, in other words, we'd like to be able to do a Fourier analysis of the output of the ADC, just like we did for an amplifier. Let's see what's involved. Before that, let's recall that a discrete time sequence, which is periodic with a period of p samples, can be expanded into a discrete Fourier series. However, unlike in the continuous time case, a discrete time Fourier series consists of only p sinusoids. The fundamental frequency of the Fourier series expansion is 2 pi over p radians per sample, and the fast Fourier transform is simply a rapid way of computing the Fourier coefficients. Now, some jargon. P, the period, is often called the FFT record length, and since the samples are generated by taking a continuous time signal and sampling it at Fs, the fundamental frequency of the Fourier expansion, namely 2 pi over p radians per sample, when translated to hertz, becomes Fs over p hertz. This is often called the binwidth of the FFT. Now, let's see what it takes for the frequency of the input to result in a periodic output of the ADC. If the input frequency is denoted by Fin, after sampling, the sequence is 2 pi times Fin by Fs times n. This sequence is periodic only if 2 pi times Fin by Fs times p is an integral multiple of 2 pi. In other words, the discrete sequence that results from sampling a continuous time sinusoid is only periodic if Fin by Fs is a rational number. This is an important deviation from continuous time where any sinusoid is periodic. So, another way of saying this is to say that P over Fs is m over Fin, and this means that in one record length, you must have an integral number of input cycles. Now, given that we understand that Fin by Fs is a rational number, an obvious question is any rational number a good choice? To show you why it is not so, let me consider an example. I'm going to choose Fin by Fs to be 1/4, which is as rational as any number can get. Now, I'm going to take a pure sinusoid at 1/4 the sampling rate and pass it through a really bad quantizer, right, which has only 3 levels, 1, 0, and -1. Now, if I take a pure sinusoid and pass it through a quantizer, I would expect to see a whole lot of distortion at the output because the quantizer has got only 3 levels. Let's see what happens for this particular choice of input frequency. Cos 2 pi Fs by 4, which is the input frequency, times t is the input, when sampled at Fs, results in cos pi n over 2, which is 1, 0, -1, 0, and so on. It passes through the quantizer, and voila, the output is 1, 0, -1, 0, which is the same as cos pi n by 2, which is the input. So, I have here a situation where I have a really bad quantizer, I put in a pure sinusoid, and I get 0 distortion. There's certainly something strange going on here, and the reason is the following. Mathematically, one can understand this by interchanging the order of the quantization and sampling operations. Quantization, being a nonlinear operation, will cause harmonics of the input tone to appear at the output. So there will be Fin, 2Fin, 3Fin, and a whole bunch of harmonics. After sampling, many of these harmonics will alias into the frequency range 0 to Fs over 2. Thus, if you don't judiciously choose the input frequency, then many harmonics can alias on to the same bins and therefore make it appear as if there's no distortion. For the specific case of Fin being 1/4 Fs, it's easy to see that all odd harmonics of the input frequency will all alias to Fs by 4. So the third harmonic is 3Fs by 4. It aliases to Fs by 4, and which is the same as the input signal. And therefore, this is why we are seeing zero distortion, even though we have a very bad quantizer. So the moral of the story is therefore to choose the input frequency so that its significant harmonics do not all alias to the same locations. Now, to summarize therefore, Fin by Fs must be rational, and to prevent aliasing of the significant harmonics, one should choose M and P, namely the numerator and denominator, to be relatively prime. For purposes of computing the FFT, it is often convenient to choose the record length, namely P, to be a power of 2. So you often have Fin to be M by 2 to the Q times Fs. And another piece of jargon that you often hear is that the input tone lies on a bin when these conditions are satisfied. As an example, if one wanted to test a 6-bit A to D converter running at a gigasample per second, you want to test something roughly at Fs by 4, you should not choose the input frequency to be exactly 250 megahertz. That will make even a very bad A to D converter look like a perfect one. So a good choice, for example, would be to choose a record length of 1024 samples and make M, the numerator, 253, so you get an input frequency of 247 point blah 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 megahertz. Right? It's also important not to round this number off. And this also, I don't know how many of you have got a chance to take a look at ADC data sheets. And if you look at the output spectrum, you will see the input being some strange frequency like 247.07 blah blah megahertz, right? And the reason for choosing that is to get M and P to be relatively prime. So if you wanted to test an A to D converter, you would make the input and the clock be in sync, and this leads to the obvious question of what happens if, I know they should be in sync, but what happens if they're not in sync? So in other words, the input and Fs are not rationally related. Before we get there, let's quickly remind ourselves of the implications of computing the FFT of a p-point sequence. Whenever I compute the fast Fourier transform of a p-point sequence, this is what I'm implicitly doing. I'm assuming that these p-points form one period of a discrete time periodic signal with period p. Actually, the FFT is kind of a misnomer because it's not really computing a Fourier transform. It is actually computing the Fourier series, so a more appropriate name would have been FFS. Okay, so let's take a look at what happens when the input is on a bin. As we discussed earlier, in this case, the input sinusoid will exactly have an integral number of cycles in one record length. If the input does not lie on a bin, as you can see, there are not an integral number of cycles, and therefore there's a discontinuity in the periodic waveform, which is the periodic extension of these p samples. Whenever there's a jump in the time domain, we all know that there will be a lot of high frequency energy because of the impulse. And there will be spectral energy everywhere, and this is what is called FFT leakage. And is shown in this slide. The blue spectrum is the FFT of a sinusoid where the input tone lies exactly on a bin, and as you can see, only one of the FFT bins is non-zero. When the input is off of a bin, you can see that energy leaks everywhere, causing it to look like the Eiffel Tower. Now, why is leakage problematic? When there is no leakage, as you can see in this example ADC output spectrum, it's fairly straightforward to figure out which is the input signal and which is the quantization noise. With leakage, you can see that separating the input and quantization noise is not a very straightforward affair. So, what do we do about this? The solution is motivated from the fact that the problem area is the end of the record. So, the discontinuities at the ends of the record length are what are responsible for FFT leakage. This means that to solve this problem, one would have to pay less attention to the record length, to the data at the end of the record, and more weightage to the data in the middle. And that's precisely what is done in practice. So one can take the input data sequence, where the input does not lie on a bin, and multiply it by a window function, which is high in the middle of the record, and tapers down close to zero at the ends of the record. Once you multiply the input sequence with a window, the resulting sequence is this. When you make a periodic extension of this sequence, the discontinuities, as you can see, are gone. Therefore, one should expect less high frequency energy when one computes the spectrum of this sequence. That was a time domain intuition on why there is leakage and what one can do to mitigate it. It can also be seen in the frequency domain. Consider a sinusoid at a frequency omega naught. This is an infinite length sequence and has a Fourier transform which consists of two delta functions at plus and minus omega naught. By looking at a finite number p samples of this infinite length sinusoid, what one is doing is effectively multiplying this sinusoid by a rectangular window of width p. Multiplication in the time domain, as we all know, is equivalent to convolution in the frequency domain, and therefore the Fourier transform of this p length sequence is the delta function centered at omega naught convolved with the sinc function which has nulls at multiples of 2 pi over p. When you convolve these two, you get a Fourier transform which is centered at omega naught and has nulls at multiples of 2 pi over p from omega naught, as shown in this slide. Now, the FFT is simply nothing but the sampled version of the Fourier transform of the sequence. So, when one computes the FFT of these p samples, what one is doing is essentially sampling this sinc function which is centered omega naught. If omega naught lies on a bin, then one would be sampling the peak and the nulls of the sinc function, thereby resulting in an FFT with only one non-zero bin. If the input lies off of a bin, as you can see in this picture, when you sample the Fourier transform, you get the Eiffel Tower. The solution to this, as we saw earlier, was windowing, where samples at the edge of the record are weighted a lot less than samples in the middle of the record. And the fact that this is varying much slower than the rectangular window means that the Fourier transform of this window function will have much lower high frequency content as shown in this picture. Therefore, when one computes the Fourier transform of the windowed sequence, it has a wider main lobe and much lower side lobes as shown here. So this shows an example of how windowing mitigates FFT leakage, and that the spectrum here in red is the FFT without using a window. In other words, you're using a rectangular window, or you're weighting all the samples the same. The spectrum in blue is with the windowed sequence, and as you can see, leakage is greatly reduced. Given that the general idea of having a window is to weight the samples in the middle more than the samples at the edge, one can come up with any number of windows, and they're all, I've listed a couple of commonly used ones. The rectangular window is one where you don't do anything at all, and you can see that the response at high frequencies is not very low. The raised cosine of the hand window has better high frequency response, and the Blackman-Harris window has even higher frequency attenuation. Another thing you can observe is that the main lobe width, which is how wide this is, and the side lobe suppression, namely how much attenuation you get far away, there's a trade-off between these two. That turns out to be a fundamental trade-off. Another common source of doubt is the difference between the pass spectral density and the FFT. I'd just like to quickly mention that if you had a long record length, say of 4 NFFT points, one way of computing the pass spectral density would be to divide this record length into multiple chunks, each with a record length of NFFT, compute the magnitude squared of the FFTs of each of these chunks, and simply average them. And that happens to be the pass spectral density. So this kind of covers what I wanted to say about spectral estimation for Nyquist rate data converters. Next, I will move on to the simulation of delta sigma converters. Delta sigma ADCs are stiff simulation problems in the sense that the input frequency is low and the sampling rate is very high because of the oversampled nature of operation. Further, there is no one-to-one correspondence between the input and the output. In a Nyquist converter, for instance, you put in an input and the output sample must resemble the input on a sample-by-sample basis. In a delta sigma converter, it only resembles the input in the average sense. So debug is not quite trivial. Computing the SNDR is a little more involved than the Nyquist case, and simulating device noise, for example, is computationally very, very expensive, and we'll see how we can get around some of these limitations going forward. The basic idea behind an oversampled data converter is to embed a coarse quantizer inside a negative feedback loop. If the loop filter L has high gain at low frequency, then negative feedback forces V and U to be close to each other at low frequency. If you do the math and represent the quantization error by E, we see that the output Z transform is L by 1 plus L times U plus 1 by 1 plus L times E. The transfer function from the input to the output is called the signal transfer function, and the transfer function from the noise source to the output is called the noise transfer function. As the loop filter gain is very high at low frequency, we see that at low frequencies, the signal transfer function is approximately 1, and the noise transfer function is approximately 0. Thus, it is possible to obtain an extremely high in-band signal to quantization noise ratio, even by using a very poor quantizer. Now, choosing an appropriate loop filter transfer function L is the first step in the design of a delta sigma converter. simplistically speaking, if the gain of the loop filter is not very high, then there is not enough noise suppression. On the other hand, if one chooses L to have too high of a gain in the signal band, then because of the negative feedback, it's very likely that the loop becomes unstable. An example of a noise transfer function, which is basically a high-pass filter transfer function, is shown here. You can see that the gain of the noise transfer function is very, very small inside the signal band. The signal bandwidth is denoted by B, and this quantity Fs over 2B is often called the oversampling ratio, or the OSR, which is a very common acronym you will come across in delta sigma work. This shows example input and output waveforms, and you can see that the input continuous time waveform in red and the output sequence in blue. It's visually not apparent, of course, that the output resembles the input in any way, but when you compute the spectrum, you can see that in the signal band, the signal to quantization noise is very, very high, and at high frequencies, there's the shaped quantization noise, which is the quantization noise which has been high pass filtered by the modulator. Now, one of the fundamental attributes of a delta sigma converter is what is called signal dependent stability, and the intuition behind that is the following. The output of the delta sigma loop is the signal transfer function times U plus the noise transfer function times E. At low frequency, the signal transfer function is approximately U. So the input to the quantizer, which is basically the output of the modulator plus the quantization error sequence, must be NTF minus 1 times E. In other words, the input to the quantizer, which is inside the delta sigma loop, consists of the input plus some shaped quantization noise. Now, as the input U approaches the saturation limits of the quantizer, the shaped quantization noise will start to saturate the quantizer once in a while. Once the quantizer saturates, the quantization error increases, that propagates around the loop and saturates the quantizer even more, and so on until the input to the quantizer becomes very, very large, or technically the modulator has become unstable. So signal dependent stability is something to be expected when one has a nonlinear system in negative feedback like a delta sigma loop. The stable input range divided by the quantizer range is often referred to by the acronym MSA, which stands for the maximum stable amplitude. And as you can imagine, the maximum stable amplitude depends on many factors: the number of quantizer levels, the noise transfer function itself, and the input frequency. The DAC, which of course results from realizing a quantizer. A quantizer, recall, is an ADC and a DAC in cascade. The DAC, in many cases, is also not quite linear, and that's because of device mismatch effects in the DAC. Therefore, the code versus analog output characteristic is not quite the straight line that you want, but something as shown in red. Now, negative feedback will force this analog signal to track this at low frequency. However, because of the nonlinear characteristic of the DAC, it follows that the digital input code must be nonlinearly related to the input, thereby causing a degradation of data converter performance. So to prevent this, a commonly used technique is what is called dynamic element matching. And for our purposes, we'll just imagine it to be some kind of magic box that shapes mismatched noise outside the signal band. A more generic single loop modulator is shown here. The loop filter has two ports. One is the input port and one is the feedback port. The noise transfer function can be shown to be 1 by 1 plus L1, and the signal transfer function can be shown to be L0 by 1 plus L1. In a discrete time realization of the loop, the loop filter and the DAC are realized using switch capacitor circuits. It is also possible to realize the loop filter using continuous time circuitry, and that then the sampling occurs at the output of the loop filter rather than at the input. Continuous time operation has several advantages, one being the so-called implicit anti-aliasing feature of the delta sigma loop. Namely, if you put in inputs here at multiples of the sampling rate, unlike in a Nyquist ADC where you'd need an anti-alias filter, that anti-aliasing is implicitly built into the structure. Continuous time delta sigma converters are also easy to drive because of the resistive input impedance that they offer, and they also, like most continuous time circuits, have reduced demands in the slew rates of the op amps. The linear models of discrete and continuous time delta sigma modulators are shown in this slide. In the discrete case, the input is sampled right up front, processed through some transfer function, which is that L naught by 1 plus L, which is called the signal transfer function. This sequence is corrupted by shaped quantization noise and results in the output sequence. In the continuous time case, the input is passed through a continuous time transfer function, the signal transfer function STF, before being sampled and corrupted by shaped quantization noise. So the design flow of a delta sigma ADC would be to choose the oversampling ratio, the number of levels, the noise transfer function, and the architecture, and determine the maximum stable amplitude using simulation. One would then go ahead and determine the component values and design the building blocks of the modulator, namely the loop filter, the ADC, the DAC, and the DM logic. Example building blocks in the case of a discrete time modulator are switch capacitor integrators, comparators, which whose offset and delay need to be controlled, and the feedback DAC, which is most often a switch capacitor kind. In the continuous time case, continuous time integrators are used. Feedback DACs can either be switched current, switched capacitor, or switched resistor. Several high-level design aids are available for delta sigma modulator design. Something I really like is the delta sigma toolbox of MATLAB written by Dr. Richard Fryer of Analog Devices. It's a neat set of routines that enable high-level design and rapid simulation. You can find SNDR, maximum stable amplitude, etc. And it's an engine for simulating a discrete time modulator given the loop filter description in state space form. So in other words, if you can describe the loop filter using the 4 state matrices A, B, C, and D, then you can compute V as a function of U with very conveniently and rapidly. It also supports multiple inputs and multiple quantizers and can be combined with the numerical power of MATLAB to design even continuous time designs. Overall, all linear effects can be easily modeled with the toolbox, and with minor modifications, even non-idealities like offsets in the quantizer, etc., can be modeled. It's a great tool which lowers the barrier of entry to delta sigma modulator design and understanding, and is therefore of a tremendous educational value also, and I'd highly recommend it. Once you've done the high-level design, then the next part is to actually build the circuits and put the whole thing together and make sure it works as you think it should. So a common strategy is to keep one block real and all others behavioral, namely either Verilog A or what have you. This isolates gross problems like clock phasing errors, coefficient scaling errors, and so on. Then I would typically make 2 blocks real, and this will make interface issues come out if there are any. And as I said, you must always run the complete design at the transistor level, because many problems are often subtle and only show up at this level. So the things that you would want to simulate in a delta sigma ADC are the in-band SNR. So the question to ask is, how do I calculate this? And how long of a simulation must I run to be able to estimate this SNDR accurately? And what should I do with windowing and so on? So let's dive into this. As we just saw, the output of the delta sigma ADC consists of the signal plus the shape noise. One thing we can do based on our experience before is to say I'm going to put the signal on a bin. Therefore, there are an integral number of input cycles in one record length. So what we are left with is the shape quantization noise, which is a pseudo-random signal. Now let's see what happens if I simply use a rectangular window to compute the spectrum. I think I should be okay because the input lies on a bin after all. However, the Fourier transform of the infinite length shape noise sequence must do this because it's a high pass transfer function. In the signal band, the amount of energy is very, very, very small. Now, because of windowing, the spectrum of the windowed sequence is this spectrum convolved with the sink because of the rectangular window. And as you can see, when you convolve this waveform, this spectrum with this spectrum, you get this because, for instance, energy here will leak to the side and fill up the in-band bins. So you would expect to see that the in-band spectrum is filled up with leakage from out-of-band noise rather than fundamentally from the ADC itself. So, as shown here, this is a delta sigma sequence without any special windowing. In other words, we use a rectangular window. And as you can see, the in-band is completely corrupted by leakage effects. To reduce leakage effects, just like we did for the Nyquist case, you must use an appropriately chosen window. This shows an example of a hand window where, thanks to the tapering off of the window weights as you get to the end of the record, the in-band spectrum is very small and reflects the true performance of the ADC. So for delta sigma simulations, it's not only necessary, it's not just sufficient if the input lies on a bin. You must also make sure that the shaped, you must window the data with an appropriate window to prevent the in-band noise from getting corrupted by leakage effects. The next question is, how many samples do I need to get a good estimate of the in-band SNR? Let's say we choose a record length of n samples. The number of bins, these n samples correspond to the entire frequency range from 0 to fs. So the number of bins in the signal band must be n by twice the oversampling ratio. In other words, the number of bins which we have to estimate the in-band SNR is actually quite small, especially if the oversampling ratio is high. The input signal plus 2 harmonics, assuming a hand window, will occupy 3 bins each, so that's 9 bins. DC offset consumes 2 bins, so the number of bins we actually have to estimate noise is actually n by 2SR minus 11. And it's often good practice to have at least 15 bins to estimate, to get a good estimate of the shape quantization noise in the signal band. So that means that this leaves us with n being approximately 52 times the OSR number of samples. A good rule of thumb for delta sigma simulation is to choose a record length to be at least 64 times the oversampling ratio. This means that you'll end up spending a lot of time simulating the modulator. The next thing is the following. I'd be very curious. Okay, I've simulated my delta sigma converter. It looks kind of okay. What noise transfer function have I actually realized as opposed to what I wanted to realize? So one, the importance of the noise transfer function is not to be underestimated. If the noise transfer function deviates too much from the desired value, then it's basically trouble. It's entirely possible that your modulator will be unstable or is close to instability. And one common thing that a lot of people do is to just eyeball the spectrum. And the idea behind that is the following. If the output pass spectral density consists of two quantities, that's the spectrum of the input signal plus the shaped quantization noise. And as we assumed earlier on in this tutorial, it's common to assume that the quantization noise spectrum is white. So in other words, one could say, hey, I look at the output sequence, eyeball its spectrum, and from the shape of the spectrum, I could infer the noise transfer function, because if this is white, PSD of E is flat. So if untoward things are happening, hopefully I should be able to catch it by looking at the spectrum. Unfortunately, that's not often useful, as I'll illustrate with this example. This is an ideal second order delta sigma modulator with a single bit quantizer. Now I'm looking at the spectrum and I see strange things happening. There are tones at fs by 2. Now, as a designer who's designing his first delta sigma converter, I'm thinking, is this me? Is this the quantizer? Is it layout parasitic? Is it my op amps are not good enough? What is going on? Right? And eyeballing the pass spectral density can be misleading, because often the PSD has so much variance that it's impossible to discern what is happening in the modulator. However, this can be fixed in simulation by using the following approach. The output, as we saw, is the signal transfer function times U plus the noise transfer function times the quantization error. The quantization error is this sequence minus that sequence. In a physical modulator, when the chip comes back, you have no access to the input of the quantizer. However, when you run simulations, you do have access to that quantity. So the output can be exactly written as STF times U plus NTF times V minus Y. So there's no approximation here at all. The error we're making is in thinking of this quantization error to be white. So, and that's apparent the moment you start looking at the quantization error spectra, and this is what you see. You can see that the quantization error is neither white, and it's got strange tones at fs by 2, and that's what shows up at the output. So it's not really your fault. Since the quantization error sequence is actually known in simulation, one needn't assume that the PSD of the quantization error is white. One can actually use the PSD that's there from simulation. So dividing the PSD, pass spectral density of the output sequence, by the pass spectral density of the simulated quantization error sequence, one can get a much better estimate of the noise transfer function. And that's what I'll show in the next slide. When I divide PSD of V by PSD of E, this is what I get. And you can see that this is devoid of any, within quotes, randomness at all, because we do have access to the input sequence, which is E. Another example, this slide shows two pass spectral densities. This corresponds to two modulators. One has an unintended feedback delay of 1/10 of a bit period. But however, as far as I can see, I can't discern any difference between these two PSDs. Both of them pretty much look identical to me. However, the moment I plot PSD of V by PSD of V minus Y, you can see that the modulator with an extra delay definitely shows, you can see a peaking in the noise transfer function, which makes sense because of the excess delay, right? And so therefore, this is a nice way of figuring out if your modulator is doing the right thing. The next thing I'd like to simulate are the signal transfer function and device noise. before we go there, let's take a brief digression and kind of understand the role of RF analysis in delta segment ADC design. A typical RF designer's simulation arsenal consists of the periodic steady state, periodic AC, transfer function, and noise analysis. The question is, why and where are they relevant in ADC design? Periodic analysis pertain to systems described by linear differential equations with periodically time-varying coefficients. In our line of work, they most probably refer to linear networks where there's periodic switching activity like switch capacitor circuits. And why are they important? Recall that all A to D converters are fundamentally linear, periodically time-varying systems if the quantization noise is set to 0. That's because of the sampling operation inherent in every analog to digital conversion. Time domain analysis of LPTV systems is time consuming, especially with noise calculations. Frequency domain analysis yields unique insights, and more importantly, they're supported by several commercial circuit simulators. As always, it helps to know what is happening behind these tools. So, as we all know, a linear time invariant system is one where the shape of the impulse response does not change if the input impulse is delayed, as shown in this picture. The input impulse is delayed by T1, but the shape remains the same. In a linear time-varying network, on the other hand, the shape of the response depends on the time of application of the impulse, as shown in the picture on the right. So, the impulse response is denoted by h of t, which is the time of measurement, and T1, which is the time at which the impulse is launched. The output of a linear time-varying system to an input tau away is proportional to the input at t minus tau, namely x of t minus tau, and the impulse response to an impulse applied at t minus tau and measured at t. The total output at a time t is simply the sum of all such components as tau goes from 0 to infinity, and that's the familiar convolution equation for linear time-varying systems. Now, we'd be interested in what happens, what the output of such a system would be for a complex exponential input of the form e to the j omega t. I'll spare the mathematical details here, but it turns out that the output of a linear time-varying system to e to the j omega t is e to the j omega t multiplied by a frequency response. Unlike in time-invariant systems, this frequency response depends on time. And that, of course, makes sense because the gain experienced by the complex exponential must change with time as the properties of the network are changing with time. Now, a linear periodically time-varying system is a special case of a linear time-varying system where there is time invariance for special values of delay. Denoting the period of the periodically time-varying system by Ts, what it means is that if I applied an impulse at t equal to 0, the shape of the response is as shown in red. If I delay the input by multiples of Ts, the shape of the response remains the same as shown in the blue and green curves here. On the other hand, if the input was delayed by T1, the impulse response shape is different from the one where the impulse was launched at t equal to 0. But it repeats if the impulse is applied at T1 plus Ts, T1 plus 2Ts, and so on. Mathematically, this is the relationship that governs the impulse response of a linear, periodically time-varying network. Such a system is very common in our line of work because most of our circuits are periodically switched with a clock frequency. Now, the time-dependent frequency response of a linear, periodically time-varying system is basically, in simplistic terms, the gain experienced by a complex exponential as a function of time. If the properties of the network are varying periodically with time, it makes sense that the gain experienced by the complex sinusoid also varies periodically with time. Therefore, it means that the time-dependent frequency response is varying, has a period of Ts. Now, anything which is periodic can be expanded as a Fourier series. This means, therefore, that the time-dependent frequency response can be expanded as follows, where the fundamental frequency of the Fourier expansion is 2 pi over Ts, where Ts is the periodicity with which the LPTV system is varying. Therefore, if the input to an LPTV system is e to the j omega t, then the output is of the form h sub L of j omega, which are the coefficients of the Fourier expansion of the gain multiplied by e to the j omega plus L omega s. In other words, what this is telling you is that unlike in a time invariant system where an input at omega results only in an output at omega, in a periodically time varying system, an input at a frequency omega results in output frequency components not only at omega, but at frequencies of the form omega plus integral multiples of the sampling rate. So, for example, if I put in a tone at omega here, in the output spectrum, there is a tone at omega with some gain h sub 0. There is a tone at omega plus omega s. There is one at omega plus 2 omega s, and so on. The gain from the input frequency, the output frequencies, are what are the outputs of what is called the periodic AC analysis, which is a common RF analysis tool. This number L is called the sideband, and that corresponds to the number of multiples of omega s that you need to add. By the same token, if the output of an LPTV system consisted of a sinusoid at a frequency omega, it could be resulting from inputs at multiple frequencies. In other words, a tone at omega will result in some output at omega naught, at omega. This could be also the result partly from a tone applied at omega plus omega s. Some part of it could be from omega plus 2 omega s, and so on. The gains from these sideband frequencies to an output frequency is computed using what is called the periodic transfer function analysis. Now, we have seen, therefore, that frequency translation is an inherent property of linear periodically time varying systems. And since they apply to signals, they must also apply to noise, and therefore, the noise at the output of an LPTV system at a certain frequency omega has to be computed taking into account all these frequency translation effects. And that is precisely what is done in the periodic noise analysis, which is often called P-noise. Okay, so how is all this relevant to delta sigma converter design? Let's see that. As we saw before, as an example, I'm taking a continuous time modulator. The linear model of a continuous time modulator is as follows. The input is filtered through a transfer function with frequency response STF of f, which is sampled and corrupted by shaped quantization noise. So, when we say I want to find the signal transfer function, what I'd like to do is therefore to find the frequency response STF of f. There are at least two ways of doing this. One is to take the delta sigma modulator, put in the input tone that you want to measure the frequency response at. You run the modulator for a long time, you collect the output data samples, perform an FFT. This will consist of the input signal plus the shaped quantization noise. And you can keep doing this for every frequency that you want to measure the response at. Now, this takes very long if you want to do this over a large number of points. Further, the amplitude of this tone has to be carefully chosen because if you choose the amplitude to be too small, the sinusoid could be swamped by shape quantization noise. If it is too large, you will make the modulator unstable. However, the advantage of this is that you get the true signal transfer function, which accounts for the signal dependent gain of the quantizer. Another way of doing this is to use the periodic transfer function analysis. To perform this analysis, however, one needs to make sure that the system you're simulating is actually a periodically time varying one. Unfortunately, a delta sigma modulator has no periodic steady state in the sense that because of the presence of the quantizer, it's virtually impossible to get the simulator to converge in the PSS analysis. This can be fixed by removing the quantization noise source. In other words, if you replace the quantizer by a sampler, then you have a system where you have artificially set the quantization noise to 0. And once you do this, you now have a linear periodically time varying circuit which is amenable to periodic steady state and therefore periodic transfer function analysis. And this yields the signal transfer function assuming a unity quantizer gain. This shows an example setup of periodic transfer function analysis. I took an example where the sampling rate of the modulator is 400 kilohertz. I'd like to measure the signal transfer function in the range 0 to 1.5 fs, and therefore I choose the basic frequency band to be 0 to fs by 2, and I choose to get one sideband out that basically will yield the signal transfer function in the range 0 to fs by 2, which is this range, plus sidebands 0 and 1, and for both positive and negative frequencies. The output of the modulator has to be sampled to be of relevance because it's a sampled output which is what we're interested in. So the tool will figure out, you can specify when you want to sample the output. And this shows the signal transfer function obtained using such an analysis. This is a second order continuous time delta sigma modulator where the sample and hold has been replaced, where a sample and hold has replaced the quantizer. As I indicated earlier, a continuous time modulator has nulls at multiples of the sampling rate, so the signal transfer function is virtually 0 when the input frequency is equal to fs. The next thing is to simulate device noise. There are two ways again of doing this. One is what is called the transient noise analysis, which a lot of CAD vendors now show the capability of running. The idea is very straightforward. You just add a noise source in parallel with every device. And since you have control over the spectral density of the noise that you're adding, the spectral density can be bias dependent, what have you. This noise waveform, so to speak, is updated at every simulation step, and it's quite straightforward to model white and colored noise. However, one has to be careful to interpret the results, and more importantly, it's extremely expensive with respect to simulation time. One thing you could do is if you have a server farm, you can run many instances simultaneously and average the result. But this is not useful for design iteration, I guess. And how white noise is generated is by generating Gaussian random variables and then creating a waveform like this, where the noise stays constant for a small amount of time, delta t. The true spectrum is not really white because of the hold operation for delta t. The path spectral density is a sinc square type of roll-off. So the actual spectrum of the white noise source generated is has a sync roll-off as shown here, and as long as your circuit bandwidths are somewhere here, this is a good approximation to white noise. This is immediately telling you that in order to be able to simulate use transient analysis properly, you need to be able to simulate at very small time steps, and that results in very large simulation times. As an example, this is a toy circuit with 1 kilo ohm and 1 nanofarad, and I'd like to run transient noise analysis to check the output spectrum. The transient noise analysis also has has an option where you can deliberately numerically increase the noise generated by a large factor. This way, the noise floor of the computer you're using does not affect the results. And once you have the output noisy waveform, you can do pass speckle density estimation, and this is the command you can use in MATLAB to do it. And as you can see, the results, unless this waveform is sampled with sufficiently high resolution, the aliasing effects of sampling can cause inaccuracies. For example, this output waveform, which has a bandwidth of 160 kilohertz, is sampled with 500 kilohertz, and you can see that because of aliasing, the in-band noise spectral density has increased, whereas if I increase the sampling rate, you get the value which is about 4 nanovolts per root hertz, which is that corresponding to a 1 kilo ohm resistor. In a delta sigma modulator, again, one could run transient noise analysis because one cannot find a periodic steady state due to the comparator inside the loop. This again, as I said, is very time consuming. If one wants to use the periodic noise analysis, one can do so. But before we do that, let's remind ourselves of the following. The in-band noise of a delta sigma modulator is usually dominated by thermal and 1/f noise of the front-end stages of the modulator. In any good modulator, quantization noise is about 12 to 15 dB lower than the thermal noise, and therefore most of the noise should be coming from the loop filter. In other words, the quantizer should be a very, very, very small contributor to the in-band noise. As an example, I took a transistor level example with a 2-stage op amp and a comparator as shown here. The circuit details are not important, and I ran a transient noise analysis, and as you can see at the output, the in-band is dominated by thermal and 1/f noise sources. There is also shape quantization noise, which in the signal band is much lower than these noise sources. I have deliberately put the input frequency outside the signal band so as to be able to get good visibility on the in-band spectrum. And as you can see, this takes a while. This particular simulation took 17 hours to run. Okay, so is there a way of running to compute noise effects in such ADCs rapidly? And as we saw, the inability to run a periodic steady state is the reason why we cannot use periodic noise analysis. So that can be overcome by replacing the quantizer with a sampler, and this way we have a linear network which is periodically time varying. One can therefore run periodic noise on this, and here is an example setup. This is the fundamental frequency of the LPTV system, which is the sampling rate of the modulator. It is 400 kilohertz. This is the start and stop frequencies, and I'm specifying that I should account for 10 sidebands of noise aliasing. And this is the comparison of the results of transient noise with periodic noise. And as you can see, in the signal band, there's a very, very good match between both these analyses. Of course, at high frequency, the periodic noise analysis gives you much lower noise, and that makes sense because the linear circuit does not have any quantization noise effects. So, to summarize, we saw a quick overview of data converter architectures, namely the flash and pipeline ones. We spent some time on analyzing and understanding spectral analysis for A to D converter design. Then we saw techniques for estimating the in-band SNR and noise transfer function in delta sigma converters. And lastly, we looked at the use of RF analysis in mixed signal simulations, specifically in delta sigma converter simulations. So to close, every ADC and DAC has its own design and simulation challenges. It's common to use behavioral models and simulation during analysis and design iteration. During design debug, you might want to use a mixture of transistor level and macro models. And the use of RF analysis is actually a very nice way of reducing simulation time in many converters. These are the references. The ones in blue are those that I particularly like and are written very, very well. Ken Kundert's paper on RF simulation and its applications is a nice introduction to the way RF analysis work. And his website also has got a whole bunch of macro models that you can use in Verilog A. Several macro modeling tools are also available. MATLAB and Simulink and the Schreier toolbox are of course very commonly used. I'd also like to mention here CPP Sim, which written by Mike Perot here. It's extremely versatile and useful tool that I'd urge all of you to try out. So thank you for your time and attention, and I think we're just in time for lunch.